So now I have a pleasure to introduce the plenary lecture that is going to be given by Chronis Kynigos, professor at the University of Athens. Chronis is well known for his research on digital tools and his particular interest in constructionist learning environments for mathematics meaning making. Recently, he was leader of two successful European projects on mathematical creativity with technology, MC², and a couple of years before Remath project with digital tools. So we are looking forward to your talk in which you will share with us your reflections on designing for mathematical meaning making. So it's to you, Chronis.
Bit better now? If you can't hear me, just put your hand up. So we have a lot of slides to go through and a lot of things to see moving and manipulated on the screen. I have things to show, stories to tell, and problems to share today. So to begin with in those of us who are working in the uses or finding the uses of digital technologies in mathematics education have quite a tall order. We have a legacy which began 50 years ago and which asks for a lot of things, and I feel that we have been very impatient. Recently I was in a plenary lecture by Andy DeSessa, the title of which was "Imagine if your project could last for 100 years. How would you plan for instigating change and researching on what is to be done?" So we are asking for a lot of things. For instance, we are looking to generate environments, as Papert said, that are rich or dense in opportunities for mathematical meaning making. We perceive digital artifacts as expressive media. When I read Richard and Celia's paper in, I think it was 2003, it sounded like a good word, but since then it has become more and more a tool in my thinking. It's not obvious, it's where we come from, but not everybody perceives of technology as a medium with which to express mathematical meanings. We look at digital media as a tool with which students may access powerful mathematical ideas that otherwise are inaccessible or obscure by traditional methods of expression. And we also want to engage teachers in doing the impossible, in designing added value media and activities and dealing with professional, institutional, societal traditions so as to generate these environments in their own classroom on top of their job. So all these things, it goes without saying, we cannot expect them to happen in 50 years and to proliferate. And we need to think of Papert's 10%. But the point of my talk is, how do we view this 10%? Do we view it as a silo situation where we only take care of the 10% and disregard everything else? Or do we see it as a means of integrating with different ways in which mathematics can become relevant to today's society and important and mixed with other things that are of interest in the wider European setting? So we are, in mathematics education, we're looking for added value from a pedagogical point of view. We are connecting digital technologies with innovation. We question established epistemologies, institutions, we question practices and assumptions with respect to schooling. And we focus on technology for expression and meaning making. And we are also looking at teachers' knowledge, this synthetic knowledge that has to do both with domain and pedagogy, but also with the uses of technology. So my own recurring concern throughout these years was whether there is a sense in thinking inside the box, thinking as a mathematician, as a mathematics educator, and thinking as someone who needs to continually design and implement through design research the way things might be in the future, or whether there is a relevance and scope in creating integrations at different levels, not just the research and the theoretical level, but other levels as well that we'll see, and having an element of my efforts in that. And the reason why that happened, it's not surprising, is all this history began from a large European network, the logo of which was to achieve scientific and strategic integration, not just scientific, and looked at the field in Europe working for the future of learning with digital technologies. I've been engaged in European projects, which means that you have at least 6 to 8 different research teams coming from different disciplines, all working together to achieve a kind of a broad goal. I've been engaged in design research and in the production of frameworks for action. We have the problem of changing sustainability models. We saw what happened with Cabri and Sketchpad. The technological infrastructures are changing, and the sustainability models of the tools that we use are changing, and a lot of wonderful ideas are disappearing just because there isn't the impetus and the strength to keep up with what is required to allow these tools and microworlds to run. And also, the other thing I have felt which is changing is the interest in education with respect to different things. For instance, there's been a wide interest in collaborative learning, and we've been challenged to think about mathematics within that context, within collaborative learning. There's been a wide interest in the use of social media, in the use of huge portals with millions of resources, and why should we care so much about that? Learning management systems, etc. And also, recently it's quite prevalent, new kinds of paradigms for education, challenge-based learning, for instance, where we have wide, complex societal issues, and learning happens, and the use of mathematical ideas may happen within those issues, but the main point is to help students deal with the stress of elusive problems that have no one solution and require collaboration and addressing these problems. So there is a need, in my view, to move away from silo perceptions, and there is a societal push that diminishes the priority of what I call silo domains: mathematics, science, language, etc. At the Educational Technology Lab in the University of Athens, we've been working not just with research, but also with designing technologies that we have good collaborations, and we could see them come to fruition, participating through the ministry in large-scale initiatives where the responsibility lies to address a lot of people who may not have special teacher education or special knowledge. And how do you think when you are in a position to arrange infrastructures or to arrange teacher education courses for that, and of course in design research. So the outline of my talk today is I will tell you 4 different stories, and for each story I would like you to think, and I will be referring to 4 different kinds of challenges with respect to integration. One kind of challenge is to deal with the theory, with theoretical frames. The other kind of challenge is to think about mathematical concepts. The other challenge to think about affordances within digital media. And the other one is to understand and support teachers. Now, these fields of integration, I will draw from 4 recent projects. Before in math, we had the TELMA, Teaching and Learning Mathematics within Kaleidoscope group that gave birth to this large representing mathematics project that involved developing technologies and trying them out in school settings. There was another project that wasn't directly on mathematics education, Metaphora is from forum. It's thinking about discussion forum. It was about dialogical learning and learning to learn together. And we were engaged in research to do with collaborative learning, meaning making for mathematics within this context, and MC square that I will talk to you about. Now, a couple of things about each of these fields so that you can follow and see them in the stories. First of all, with respect to theoretical frames, I first joined this wonderful group of esteemed colleagues from Telma and Remath with the leadership of Michel Artigue, who continued work that was already going on outside digital technologies, looking at the way that theory is generated, produced, and used in mathematics education. And Michel used the metaphor of a landscape, like a tabletop, where there are different theories that are lying unconnected between them and ingrained with the context from which they came. And we saw that these theories are used, and there is a lot of diversity in the way that they are operationalized and used for research and for design research situation and contexts. So we generated the idea of didactical functionality. How do these pieces of theory get operationalized as they are transformed in order to engage in design research? We develop a language of concerns that helped us understand the stakes of researchers as they used the theories. What were they serving? Were they serving the theory? Were they serving the research group? Were they serving the need to make changes in the school? And the sensitivity to the context and the process of carrying out cross-disciplinary, cross-case research to be able to develop methods and tools for decontextualizing what we learned from working in a specific country with specific schools. Within the MC Square project, we continued to work on theory integration. I'll tell you a couple of things when we come to the story about MC Square. The difference here was that we didn't just have a tabletop with different theories lying, but we had a nested kind of field where our approach was to try and find out about social creativity as we looked at groups of teachers designing things together. So the idea was that we felt the need to use different theoretical frameworks in order to explain an elusive issue, which was the creativity in design. So there was a kind of a directionality and a complementarity, using different frames in a complementary way in order to explain something that we were looking for. With respect to concepts, we found very useful using in every situation, using these four constructs that seemingly are very different between them. Conceptual fields came from cognitive psychology from Gérard Vergniaud, but we continually find it useful in the way that we think and the way that we look at how students learn and how they use and they pick up and use and generalize mathematical ideas. The idea of restructurations, of not thinking that the way that curricula are structured in school systems is stable. It's just it just so happened that this structure froze in a particular educational system. But with the use of technologies, we need to step out of the box and think about different ways in which these concepts can be organized so that they are better placed and positioned for students to be able to use them and make sense of them. The idea of half-baked artifacts, developing artifacts for students to work with, to make explorations that are by design faulty. They're by design wanting, and so the students are put in a position to fix them or to change them. So this helps with respect to design. Students focus much more quickly on the kind of ideas that that we want, and also on the concept of this shaping, the reciprocal shaping of meaning and tool that is both inherent in Celia and Richard's book, Windows on Mathematical Meanings, and later work, but also on instrumental genesis theory. With respect to technological affordances, first of all, the idea of meshing different kinds of expressivity together. This is in the MC Square project. We had a meshing of digital storytelling with very diverse constructionist media, so teachers felt free to be able to think and generate stories and have different kinds of widgets in the story for students to use and do things with. Secondly, tools that allow for students to think of mathematical objects that are very hard to think about otherwise. We'll see an example. Tools that allow contextualizing mathematics in these complex value-laden issues, wider issues, and the idea of large portals that usually contain very closed things that are basically designed for assessment, but using the portal technology to embed constructionist media that both teachers and students can change at large scale. And finally, the fourth field is to think of teachers as designers, and think of teachers collaborating together to design. Think of these collaborations as socio-technical environments. We drew our theory from Gerald Fisher in Colorado, who was not in mathematics education, but in design. So we looked at the idea of embedding diversity on purpose by design, getting mathematics teachers to work with colleagues of different expertise so that they could cross their boundaries, learn from each other, and generate different novel ideas. So, story number one, designing C-books. This was embedded in the MC Square project. There were 6 academic partners: University of Utrecht, the London Knowledge Lab from UCL, Barcelona, Spain, Lyon, and Martin Luther University from Germany, and the University of Athens, University of Southampton. The MC Square project, what did we do? Well, the idea, the objective, was to find ways to enhance social creativity in the design of digital media for creative mathematical thinking. This was a very strange call. It had nothing to do with education, nothing to do with mathematics. What we were required was to find technologies with which we could support professionals in the creative industries. And it seems that some reviewer bought the story that we built in the proposal, that education is a creative industry, and that's how we got it. So the C-book technology that we built was a technology based on infrastructure from Utrecht, the University of Utrecht, Freudenthal Institute, and it was a technology that allowed teachers to collaborate in order to build these kind of e-books that could contain widgets that were very diverse. We also built a tool to help them collaborate. You'll see instances of this tool, which supported creativity from a distance and asynchronously. We had 4 communities of interest in different countries, and at the end we managed to not only produce the technology and the infrastructure, but also over 60 C-books spanning countries and spanning lots of different mathematical ideas that can be found on the site, and you can just click on the link and have a browse through these C-books. Now, with respect to the project, our main constructs was communities of interest and not communities of practice. A community of interest is a group of professionals who come from diverse communities of practice. So within that community, you may have 5 or 7 people, maybe 1 or 2 or 3 of them are mathematics teachers, the others have different expertise. And in each case, the expertise was diverse. We have these socio-technical environments. All of them are working asynchronously to develop a new kind of technology and the technology that supports this. And we drew, in order to understand creativity and the way it's generated in these groups, creativity in the design, not in students' work, we used constructionism, documentational approach, and boundary crossings. I'll say a couple of things about that. With respect to the documentational approach, what was important in this project, what we felt we could draw from Luc's group and Guedet's, was the idea of the ongoing process of resource design and exchange, and the schemes that were built over while using these resources. The idea of resources as living documents, in a sense, having a piece of resource and engaging in bricolage. I got the word from the way Papert used it for constructionist learning, bricolage with resources. So the status of a piece of resource, according to within this community, is not something which is accredited and ready-made and locked up and locked and finalized, but it's always open for a discussion, and it's always a tool to exchange ideas and a tool to reflect and redesign the way that teachers would work in the classroom. So the idea of thinking about these resources as expressions of technology, pedagogical, and content knowledge. So in the same way that Papert thought of microworlds and things that students built with those microworlds as expressions of their ideas, we think of resources as objects with which teachers express their ideas around pedagogy or around or reflecting on pedagogy. And also, because now we were working with a special kind of resource, which was a technological resource, and it was novel technology, we thought of we perceived of these professionals in communities of practice as engaging in constructionist activity, and the objects of construction were not just digital artifacts, but there was always digital stories and the way that they connected between them. So it was the idea of collective documentational genesis, the kind of shared meanings that developed and shared schemes about these ideas. With respect to constructionism, constructionism is a design theory, but it hasn't been used so much to be able to understand and explain the ways that teachers design with respect to the way that they construct pieces of resource, or they construct microworlds or digital media for their students. So we thought of these objects that were under construction, the digital artifacts and the mathematical stories, and the social creativity that emerged from the diversity of the community of interest. And with respect to boundary crossing, well, as you know, boundary objects, boundary crossing came from a very different field, and it was Celia first with her reading that brought it into mathematics education, where it had a very wide relevance and has been used in many different ways. The way that we found it useful was to try and explain how this diversity generated creativity in the ideas behind these C-books, how the different professionals, and I mean the mathematics teachers within these communities, learned from professionals of other expertise. And I'll show you how diverse these teams were with an example. This is a special book, one of the 64 books. We called it Curves in Space. This was the tool that they used. As you see, the red semantics are objections. The green ones are are contributions, and the gray ones are alternatives. So there were some objections in the discussion. We had 7 COI members, 124 contributions in this book, and the book was a story that developed in process. It began from this group thinking about curves in space, thinking about simulating them with airplanes and airplane trajectories, and then it changed drastically, and it ended up in a Sherlock Holmes style story. There's this professor in a lab, and there's this theft in the lab, and it's a matter of who done it, the professor or his postdoc. It was a time when my office was burgled and my laptop disappeared, so it was very inspiring. And the idea was to find out who done it by comparing the kinds of artifacts that these 2 academics had and enjoyed, and the artifacts were connected to ancient artifacts, but also had the shape of different kinds of helixes, Archimedes helix or exponential helix. So the idea was for students, by reading the story, to manipulate widgets that dealt with these 2 and try and make some connections and come up with their own solution, which was not given in the story. It was left open for the students to make. One of our research tools was to look at critical episodes of things that happened during the process, and to think of a creative idea and look at its evolutionary path. Don't have time to go into it in great detail now. So we perceived teachers as active agents, and we saw them engaging in restructurations with these new conceptual fields, thinking about curves in space and thinking about curvature as a section within the curriculum. We came up, of course, with a lot of questions in thinking about teachers as designers, thinking about collaborative design, is it worth the investment, about social creativity, how can we think about it, and about affordances enabling and supporting this kind of creativity. Now, with respect to theoretical integrations, you can see this quote from Michel Artigue and Maria Alessandra Mariotti: "Diversity in theoretical approaches is therefore coupled by diversity in empirically applying the theories." And we saw this very, very loudly in the Telma project, where we had different groups of researchers that were seemingly coming from the same theoretical background. And when we got down to engaging in real research, we saw that we were doing very, very different things in the actual practice and in operationalizing these theories to think about our interventions in classrooms. So in the MC2 project, we perceived as theories as dynamic, not as tools that are already accredited and they are there to be used, but as tools that are evolving, and they are evolving with our with the way that we are using them. We perceived as that it was worthwhile to make connections between the theories in order to explain and understand what was going on in between the interactions of these teachers. So we engaged in what Michel has called networking praxeology, in the action, in the practice of making these connections in order to explain things genuinely, not just because it was the name of the game. And that these connections too were not stable. They were happening as we were trying to make sense of what we were looking at. So the difference here with respect to the remath work is that we felt that we had a nested landscape. We had the idea that connectivities were not neutral, but they had dynamics. They were either directional or complementary. And we also thought of the object of elucidating vehicles like issues that helped us think of the ways in which we could use these theories together. And this is a real representation of theories that were used. For instance, we have constructionism was used by Greece and the UK, constructivism in France, the TPAC in France, the ATD in University of Barcelona. All these theories were really used, and all of them were used to help us employ the documentational approach and boundary crossing to understand social creativity. This is only the end of story one, but the other ones are shorter. So just to show you a little of this technology, this is a page of a C book. So it's in Greek, but you see that in amongst the text, there's two very, very different pieces of software with different representations of helixes. The first piece of software is Turtle Sphere. You'll see more about it. The second piece of software is Ulrich Kortenkamp's software Cinderella, a programmable simulation of mathematical ideas. And these things were seamless. If I go to another page, hopefully we'll see. This is a cube construction kit from DME, and it's live, and you can create 3D objects that you see here, and this is another spiral. So this was the kind of technology. You can imagine the diversity and the freedom to think and design stories and design different kinds of widgets in those stories. Okay. Now, story number 2 is about the twisted rectangle. In order to explain the twisted rectangle, and for you to understand what it is, we need to see the piece of software with which you can produce it. It looks like turtle geometry, and this looks like a square, but it's a procedure that's been executed with 3 variables, with the values of 30, 1, and 0. And then when I click on the procedure, I get this tool which is activated. It looks like normal sliders, but they are very particular sliders that don't exist in any other turtle geometry environment, and that make this a tool that integrates dynamic manipulation with programmable mathematics. So what I can do with it is I can change the size, and as this is wandering dragging. As I drag the slider, I see what happens to my procedure as the value of the variable changes. So if I change the second one, I can see something which is very normal. I can make a line of boxes with a procedure that's very easy. But what's interesting in this piece of software is that I can look at my shape from a different angle. So it's like I have a camera and I look at my shape from a different angle, and then I can put in turns in 3-dimensional space and look at what happens to my object. Yeah, so that's the idea behind the software. There are a lot of examples that are already made here. Let me show you one example of piece of mathematics which is not so easy to think of, swaying trees. So this is it's just a recursive tree. Anybody who's done turtle geometry knows about these, but it has a little skew. It's like it's bending towards the left, if you see. So if I make it larger, I can see that it's not just growing. The twigs are growing as well. Number of twigs. Yeah. So I've put a stopper, of course, because in recursion you need to put stoppers, but there is space for more twigs as it grows. And then you can also see what happens as I change the skew, and as I make it, this is changing the skew. The closer I get it to 1, the more it comes to a proper symmetric tree. Now, this is what is interesting here, is that it's very difficult to think about the mathematics of the way in which this fractal behaves and operates if I don't have this dynamic view. I can see things about fractal geometry that are very difficult to see if I have a static tool. I can see the rate with which the twigs come out, for instance, or disappear, and what this may mean for the proportional relationship between each twig. Or I can see the ways in which the tree skews towards one end or the other. Another example is this very simple procedure, but for which I've activated a two-dimensional variation tool, which allows me, if I move vertically, I can see the x variable moving. See, this is the side of a triangle. If I move horizontally, I see the other variable moving. And this variation tool allows me to do covariation. So if I try and drag this covariation so that I always get this triangle, I will soon see that I have a relationship between the linear and the angular aspects of the triangle, which is periodic. And Kostas Gavrilis, a colleague of mine, a mathematics teacher, did a very nice PhD on mathematics and periodicity. We have a paper in PME in 2006 about it. But I can see that the relationship between those two variables is periodic by just dragging and trying to keep the triangle intact. Okay, so what about twisted rectangles? And catch it from here. It's here in a microworld. A twisted rectangle is, imagine a rectangle. The bottom part is stable and the top part starts twisting. I can't do it with this piece of paper because things start to elongate, and it's something that's very difficult to visualize and to think of. But the mathematics of building it become quite easy if I use this tool. Just to look at how it turns, and then we look at the mathematics of how it's produced. Yeah, so it turns in two kinds of ways. This is of course, there's a tangent behind that, and this is why it behaves in this way. So it's something to do with triangles and trigonometry. So this tool, Turtle Sphere, by the way, we've developed it very recently. It's done with the latest kind of technology. It plays on mobiles. It plays on everything. You can save things on your PC and then load them up again. So, and I've just unscrewed my... Yeah, it's coming. So, just have to wait for a bit for the resolution. Why did I have to fiddle with the cord? It will come in a second. Yeah. So we are talking about integrated affordances in a piece of software, but they are integrated in a way which is mathematically relevant and useful. And they are integrated so with this piece of software we can imagine mathematical objects and we can see them manipulated, but we can also think about the mathematics behind them. So these are some students trying to create a twisted rectangle with some straws. The mathematics behind it is, if you think about it in a box, and if you cut the plane diagonally, then it turns, the whole thing is two triangles on different planes that have the same side. So it's just some very simple trigonometry to figure out the turns and the lengths of the turtle moving it. The way it's done is the turtle begins here, goes down to B and then to A, then finds out how much to turn, goes up, and then turns on its axis to face this way. Calculates delta gamma, and then turns again twice, down and on its axis, to generate the last turn. And we used it with 9th grade students, and in the end they did work with the formulae. We gave them a half-baked twisted rectangle where we hid the lengths of the sides, and we got them talking about it, and you can see some text here. They tried to work by putting one of the variables to 0 and seeing what happens, and then slowly starting to change it to see what the properties might be. And this is something that you can do with it. This is a lot of twisted rectangles, one on top of the other. They look like a DNA structure. The kids were talking in amongst groups, and these are the things, some of the things they generated once they figured out how to create a twisted rectangle. They called the one on the middle, I think they called it an ice cream. No, the one on the right was an ice cream, and the one in the middle was a flower pot. Don't ask me why. Okay, now this is the end of story number 2, integrating affordances. Story number 3 is about complex societal problems within which mathematics may reside. And for problem number 3, I need to show you another piece of software, which is also available on the web. This is a game. And now if I'm a player of this game, what can I do? I have this terrain, and I might want to make visits, choices. So I'm a citizen in a city, and say I want to go to the club. If I click on the club, I see in this window what the consequences will be if I visit the club. So according to different values. So one of the values is energy. I will have minus 30. Money, I will have minus 100. Hygiene, minus 1. Fun, plus 50. Social life, plus 55. Health, 0. There's no effect on health. So if I select the point, I have this effect on my aggregate portfolio of values. Now, the way the game is designed is that any choice I make will never have only positive values or only negative values. Have some positive, some negative. So I'm always up against making choices on what to compensate for before I cross a red line. And within the program, there's red lines. If I have less than social fun or social kudos, less than some value, it throws me out, I've lost. The point of the game is to stay on as much as possible. So all of these things that you've seen are programmable by students, editable. So they can change the map, they can add points. If you add points, they get added onto this database where you can put the consequences, you can add fields and choose your own fields. And for the event handling, you have Blockly language, with which it's a Scratch-like language, with which you can put the initial values or the gameplay rules. Here you have little texts. If your fun is less than 20, it says, I think you're getting bored. So the player gets a little text. And you have the end rules when the game throws you out. So this game that you just saw, in fact, we designed it with a colleague of mine, Maria Dascolia, who's an environmentalist in the environmental education lab. And we designed it so that it is a half-baked game for environmental education. The game that we gave to the students made the winner be a very nasty, from an environmental ethos point of view, player. And we asked the children if there is anything wrong with this game. And the kids got in and started to change the parameters of the game so that the winner would be an environmentally appropriate player. And this was one idea, but we have different ideas. I don't know what it's doing now. Go back to homepage. Some resolution thing. Let me try again. Here it is. Another idea is on how do you say it? The right kind of eating. Yes, healthy eating. So if I choose a souvlaki, my health will be -15, nutritional value -30, etc. If I choose bread, cereals, everything's good. But you see, the value is also pleasure. So the game can throw me out if I keep eating only healthy foods. And this was the children's choice. Yeah, so you can imagine the diversity that you may have. We have another game which is called Blackout. You're in a house and you use the different electrical appliances and you have different kinds of consequences. And we have another game that we have developed with a student who is a language student on ancient Greek. And as a player, you're somebody in ancient Athens who wants to gain more points in becoming an MP. So you visit places. When you visit places, you get an ancient Greek text, and you don't see the numerical consequences, but they are underneath. So you're supposed to guess the numerical consequences by understanding the ancient Greek text. So it's another permutation, just to show you the kind of scope that you can think about. Now, in any of these situations, there is a lot of mathematics, even coming up to game theory, in trying to figure out how to make the game really interesting. Because it can be very easily trivialized, and you need to think about the numbers and about the relationships between the different values and the kind of red lines that you put. So this is one sense in which we try to incorporate mathematical ideas in larger issues. And these larger issues are these shifting paradigms that we talked about at the beginning. I won't show you the slides because I'm eager to get into the last story. The last story is about something totally different now. Work within the Ministry of Education. There's two initiatives in the Ministry of Education which are quite long-term, and they are organized in different subjects. So I was responsible for the mathematics part of it. One initiative is in-service teacher professional development. This has been a 10-year long project through which we have created a 380-hour course to bring in experienced teachers and get them to operate as teacher educators. And we have now 98 teacher educators in mathematics education. And the other initiative is a 96-hour course on using digital technology in mathematics lessons. We've up until now reached 30% of mathematics teachers in the country, 2,700 teachers in the 10 years. So it's pretty large scale. With respect to the mechanisms that have been built to be able to reach these teachers. Where will they go? How will we accredit them? They get brownie points in their career. So it's all political, and there's a lot of things inside there. And there's, in general, there's quite a good sense of, it's one of the few things that teachers like about the ministry about their ministry. And the other initiative is what we call Digital School, which is technological infrastructure, which I would now like to show you some examples from. Digital School is here. On the left, you have the interactive curriculum books In the center, there's a big portal with thousands of digits on different domains. And on the right, there's a kind of a Facebook-like infrastructure for education, which is looked after by the ministry. And this is, has become extremely popular. It's the most visited site in the country. 400,000 new hits every month was of a count about a year ago. Sometimes for the wrong reasons. When the paper books delay in going to schools, everybody gets into this site to start looking at the books. But it's very popular. So it's the curriculum books gone interactive. In mathematics, I was privileged enough to be able to have 25 colleagues who were very good either at building things with GeoGebra or with TurtleSphere, or they were very good at pedagogical design. And what we did is we got them to build what we call micro-experiments and put them inside the curriculum books. We developed a lot of them, 1,800 micro-experiments. And if you consider that no widget was built by one person, all of them were built by one person who was good at technology and a person who was good at pedagogy. And we had very big fights at the beginning, and in the end we became friends, but it wasn't easy because everybody thought they knew better. But they were forced to collaborate. And the result is that we have a lot of productions that have really changed the meaning of book. The students read the book, and it's very dense. They see in every page 1 or 2 experiments that they can do from year 3 up to year 11. So this story is about Dimitris. Dimitris is a math teacher, normal math teacher. He did a master's course in mathematics education, however. And at the end of his master's course, I said, well, if you want to do a PhD with me, why don't you try find 3 micro-experiments of your choice and try and change them in some way that you like and use these changed versions of the micro-experiments with your students. So what Dimitris did is he found 3 of these experiments. Here's the book, by the way. And here is a micro-experiment. You click on here and you get into the whatever it is. And this particular one is Introduction to Equations. It's a very typical simulation where you're supposed to find how much x weighs, which means that you try and just leave x on one side, make it disappear from the other one, and see how much of the known weights make the balance. And Dimitris didn't like this. He thought it was too simplistic, so he built a permutation of the simulation where you can't see the weights. The weights are in these pots, but you can see numbers. There's 3 blue and 2 red weights in there. The red ones, you know how much they weigh. They weigh 20 grams. The blue ones you don't. And the question that students have here is whether the scales are faulty or whether they are working properly. Yeah? So what the students typically did is they tried to have the same number on both sides and discovered that they are faulty. So then next they tried to make an investigation, how faulty are they? And because we know that the red weights are 20 grams, they would change the red weight 3 times, and they discovered that the fault is 60 grams. And to find out how much the blue weight weighs, then they would change 1 blue weight and see how many red weights they needed to change in order to make it balance. So it weighs 40 grams. So this is the kind of strategy that they built, and Dimitris' intention was to get the kids to think of the idea of equivalence and not the idea of equation. So if you think of the affordances that he changed, this is a GeoGebra simulation. It's somebody who wasn't very technical was able to get into it. And the point was that he took it from the accredited ministry curriculum, the hardcore thing that everybody needs to abide by, but it was open for Dimitris to change. Another example is an example with a micro experiment with turtle sphere. There's a little problem here. Nick tried to create a procedure to do a parallelogram, but he didn't really manage it. Can you help him get the procedure and fix it? Okay, so the students are supposed to make experiments with dynamic manipulation and then get into the code and change the code so that it makes the parallelogram properly. Dimitris didn't like this, and he changed it and asked the kids to create rectangles that would work properly. And then as the discussion was going on in the classroom, one of the kids said, but this rectangle is now a square. So Dimitris said to the kid, well, why don't you then make a rectangle that can never be a square? And he gave that to the kids as an investigation. And we had situation where the kids, in order to make it, put a functional relationship between the two not alternate, the two subsequent sides of the rectangle, x plus 20, some kids x times 2. So the idea here is that they're working with geometry, but they thought, without their teacher telling them, to impose a functional relationship between two aspects of a geometrical object in order to express an idea of something that they wanted to build. And finally, last but not least, another micro experiment. This is very classic GeoGebra thing. You have two concentric circles, you have two diameters, you join up the A, B, C, and D, and then the question asks you what kind of quadrangle is this, and can you make a rhombus, can you make a parallelogram, etc. And again, Dimitris was not satisfied, and what he did was he recreated the program so that you have one diameter, but the other one is just a chord. And the question here is, join up the four points and tell us if what is generated is a parallelogram or not, and why not. Okay, so he's asking the kids to think about and conjecture and prove by negation. It's not a parallelogram because this thing doesn't happen. And there's another question of what happens to point K, which is the intersection of the two segments, as it moves. So this is a dynamic question. As point K moves, how would the kids move point K? They have to get the sliders to be moving and to think about what happens. And what is very interesting here is one kid, I mean, we have many excerpts, of course, but one kid that thought to create a segment between Omicron and Omicron, how do you call it? Prime, yeah. He created a segment and then started to engage in his own investigation of what happens to Omicron prime as K moves. Now, this for me was wonderful because it showed that in this classroom there was a climate where students felt that it was okay to change what the resource that the teacher gave them and make their own investigation and engage in something which they thought was interesting and fun without asking anybody. It looks like a very simplistic intervention in a GeoGebra simulation, but it's very important that the kid felt that it was okay to do this and then to present his work in class. Okay, so no more stories. Just to conclude, as you remember, in each of these stories, we were faced with these 4 fields for integration. Integrating theoretical frames to try and explain what went on. You remember, with respect to concepts, we were using the idea of conceptual fields, of restructurations, of reciprocal shaping of meanings, and of half-baked artifacts that we give the kids to get them to focus. You saw some tools with affordances that were selected and put together for their mathematical value, and not because they are in fashion or because they have some new technology in them. And sometimes they were quite diverse. In the Choiko game, we had event handling, but we had also data handling and the idea of GIS in the programming. And also with respect to teachers, the idea of getting mathematics teachers to step outside their community and start thinking up ideas together with colleagues that come from diverse places. In the group we had in the MC Square project, we had 3 mathematics teachers. We had a teacher in theatrical play, a language teacher, and a developer. So it was a very diverse group, and they slowly learned to respect each other and to take the ideas seriously. And there were a lot of tensions, of course, in order to get the story with Sherlock Holmes going and incorporating the mathematical ideas like that. So for me, what I'd like to share with you is the problematic, the reflection of the way that we work. There are challenges that we have to face ahead. Mathematics education and mathematics is not always a priority in research and in society. There are other things that are in fashion now. We are living at the age of accountability and administration, not the age of education and of creativity and meaning generation. There is a lot of push for entrepreneurship, for 21st century skills, different kinds of paradigms. So as mathematicians, we are sometimes looked as people who come from a past kind of age and are very, very focused and very silo. So how can we think of integrating, but without losing the integrity and the importance that we give to generating more mathematical and rational thinking in our society? We have integration versus rigor. How can we join up these two? Integration versus focus. I said something yesterday about an example of a classroom where the kids were working with Second Life and getting their avatar to give instructions to a turtle to build things. And they were working mostly with driving the avatar around and looking things and dressing the avatar with different clothes rather than working mathematically with the turtle. So there's a sense of having to face the situation where the kids would focus in mathematics. And the idea of integration as a mechanism to connect with other fields and to understand the context and the values of today. So in the end, I leave with the question, is it worth the investment, and can it leverage the growth of Pappert's 10% beyond the 10%? So.